Welcome to Section 2, Cryptographic Approaches for the IoT. In this section, we'll cover fundamentals of cryptography, we'll look at cryptographic modules, we'll examine cryptographic key management processes and technologies, we'll look at implementation of cryptography within the IoT, and we'll take a look at a case study, New Approaches, Blockchain for the IoT. Fundamentals of cryptography. This is an exciting topic area that has security implications across the IoT space. Cryptography is a fundamental aspect of cybersecurity, and as such, I recommend that you take the time to understand the basics of cryptography to assist in designing sound security architectures and choosing security products for your systems. Let's dive in. The term crypto has become overloaded recently with the introduction of alt currencies like Bitcoin, Ethereum, and Litecoin. When we refer to crypto as a form of protection to secure the Internet of Things, we are referring to the concept of cryptography applied to communication links, storage devices, software, firmware, and messages used within IoT products and systems. Cryptography has a long and important history in protecting critical systems and sensitive information. During World War II, the Germans used the ENIGMA machine to encrypt communications, and the Allies went to great lengths to crack that encryption. ENIGMA used a series of rotors that transformed plain text into ciphertext. By understanding the position of those rotors, the Allies were able to decrypt the ciphertext and discover the plain text. This was a momentous achievement, but took significant manpower and resources. Today, it is still possible to crack certain encryption techniques. However, it is often more feasible to attack other aspects of cryptographic systems, such as the protocols, the integration points, or even the software libraries used to implement cryptography. Well before World War II, people were using cryptographic tools to obscure and encrypt messages. The Scytale, for example, is one such tool that today would be considered more than obfuscation than encryption. Looking to tomorrow, we see new technologies on the horizon that can help implement cryptographic primitives. For example, within this section, we'll learn about how new concepts such as blockchain can be used as a tool to help secure the IoT. Blockchain, of course, is based on a set of well-known cryptographic primitives. Other new directions in cryptography include quantum-resistant algorithms that hold up against the theorized onslaught of quantum computers, and quantum key distribution, using protocols such as BB84 and BB92 to leverage the concepts of quantum entanglement to create good quality keys for use in classical encryption algorithms. Cryptography has a rich history. As we progress through this section, we'll be doing some hands-on learning. As such, it's important to begin the setup of a security engineering lab that we can use to install, configure, and try out various tools and technologies. I like to use VirtualBox, but you can use whatever virtual machine manager you wish. Install VirtualBox on your system of choice, and then install the latest version of Ubuntu as a guest operating system. You can handle dependencies for each software installation as you progress through the section. Note that I'm not going to walk you through the installation process for any of these software technologies, as there are plenty of instructions available on the internet to guide you through each install. If you've taken the time to set up your station, you now have a platform you can use as we progress through the course. We'll be discussing cryptography across our next set of videos. Let's first talk about the various security goals that cryptographic tools can help us achieve. We hope to achieve the goal of confidentiality to ensure that others cannot eavesdrop on our sensitive information. We use encryption algorithms to achieve this goal of confidentiality. There are many encryption algorithms available to choose from, but the key point to make here is to use a well-vetted algorithm. Don't think about creating your own. Algorithms such as the Data Encryption Standard or DES, Triple DES, were staples of the early days of the Internet. Now, the Advanced Encryption Algorithm, also known as Rijndael or AES, is the standard symmetric algorithm used to protect information. We'll learn what a symmetric algorithm is in a bit. We hope to achieve the goal of authentication using digital signature algorithms. Digital signature algorithms take some input data and create a signed hash of that data, so they work in concert with hashing algorithms such as the SHA family. Digital signature algorithms include a popular ECDSA or elliptic curve digital signature algorithm. We hope to achieve the goal of integrity through the use of these hashing and digital signature algorithms as well. Note, though, that you can also use message authentication code or MAC constructs. These are things like keyed hashes that intake data and a key to create a MAC. Look at HMAC as an example here. We also hope to achieve non-repudiation through the use of digital signatures. Technical non-repudiation assurances are straightforward. However, the question is always whether the assurances will stand up in a court of law. That is much harder to achieve using only technological approaches. Let's take a quick break now to discuss some of the fundamental terms you may hear when discussing cryptography. A salt is a random data used as additional input into a one-way hash function. Salting is required to defend against dictionary attacks. An initialization vector, or IV, is a fixed-size random data input into a cryptographic algorithm. IVs are often used in block algorithms to ensure that identical plaintext does not generate the same ciphertext. You can see how this would aid in cryptanalysis if the same data always generated the same ciphertext, for example, the header information in a Word document. Entropy is a measure of the randomness of data used within a cryptographic system. Higher entropy is better. Let's talk now about symmetric versus asymmetric encryption. With symmetric encryption, we are simply referring to the keys being the same on both sides. A key is fed to a symmetric algorithm such as AES, and that key is used to encrypt plaintext into ciphertext. Party B, in this example, then uses the same key to decrypt the ciphertext and recover the plaintext. A big problem with symmetric encryption schemes is associated with key management. How do you manage the secure distribution of the same key to multiple parties, and what happens when one of those parties' key is compromised? The compromise of a single party's key requires replacement of keys for everyone involved. You can see that this doesn't scale well. Asymmetric encryption, on the other hand, uses different keys for encryption and decryption. For example, using the recipient's public key to encrypt data and the recipient using her private key to decrypt that data. Asymmetric cryptography solves the symmetric key distribution problem, but introduces its own problems related to performance. In the end, a combination of both asymmetric and symmetric cryptography is employed in most cryptographic implementations that provide confidentiality services. Speaking of efficiency, let's examine some of the well-known symmetric algorithms and their performance. This is based on a Vericrypt algorithms benchmark, and you can see that AES is far and above more efficient than the other algorithms that were tested, coming in at 2 gigabits a second encryption and 1.8 gigabits a second decryption. Of course, the actual performance of your implementation will depend on factors such as whether AES is running in hardware or software, and what the performance is of the underlying system. Let's also talk about the difference between block and stream algorithms. Block algorithms input blocks of plaintext data into the algorithm for processing into ciphertext. These blocks can be of various sizes depending on the requirements of the algorithm. Stream ciphers input a continuous stream of data into the algorithm. Plaintext data is usually XORed with a key stream to generate the ciphertext after processing by the algorithm. Algorithms also employ different modes of operation. Some modes of operation can, for example, make a block cipher function as a stream cipher, for example, the output feedback OFB mode of operation. In 2011, researchers at the National Security Agency began devising new algorithms that could meet the needs of constrained devices. In a research paper published in 2015, they described the Simon and Speck algorithms. These algorithms are designed specifically with support of the IoT in mind, and both include options for various key length and block sizes. Learn more about these algorithms at the link provided. Let's also talk about hashing and digital signatures. Hashing algorithms such as the SHA family are one-way and irreversible. They should also be collision-free, which means that given two sets of data, they won't compute to the same hash. Hashing algorithms take variable-sized inputs and create fixed-size output, or hashes. Hashing is often used to disguise passwords stored on systems, and hashing is also a core component of digital signatures. Digital signatures take a hash and encrypt that hash using the private key of the data signer. Since the private key is assumed private and secured, only the holder of that key should be able to sign the data. Verification is completed by using the public key of the data signer to decrypt the hash, and then the data is run through the same hashing algorithm and compared to the decrypted hash for final verification. If any modification of the data has occurred, the hash won't verify. Message authentication codes are similar to digital signatures. For example, a keyed MAC algorithm takes as input the data to be secured and a MAC key. This results in a message authentication code which can then be appended to the original data. The recipient uses the same key to validate the data. We explained the concept of entropy at the beginning of this video. Entropy is a measure of the randomness of the data used by cryptographic primitives. A random number generator is used to create data such as cryptographic keys, initialization vectors, salts, and other variables. The RNG must be seeded with high entropy data. Entropy, for example, might be random mouse movements, or it might be generated by a quantum tool. A bad RNG results in bad cryptographic variables and opens a system up to attack. Now, let's begin to put our lab to use. Start up your VirtualBox instance with Ubuntu. Install the latest version of OpenSSL. You can download it from the link here. Install per the directions on the site. In our next slide, you'll start working with the OpenSSL tool. The first thing we'll do is use OpenSSL to generate a RSA key pair. To generate a key pair, use the command here. This generates a 2048-bit key pair that is protected with a private key. The key pair is saved to the private.pem file on your system. Keep it in a safe place and ensure that no one else has permissions to read it. Next, we'll extract the public key from the private.pem file. Remember that public keys are designed to be shared with others, so no protection is required. Use the command here to extract the public key to the file public.pem. Now, let's hash a file. Choose any file in your system and run the command here, digest to SHA-256 on your file. This will generate a 256-bit hash of your file. We'll now use this hash as the input to a digital signature operation. Use the digest sign command here with a pointer to your private key file to digitally sign the hash. Now, explore a bit. Use the command help to see a list of other operations available within OpenSSL.